Swayam Prabha. Digital India. Educated India.
So, hello everyone, and a very good afternoon to all of you present here. So, my name is Umang Goswami, and I work as a research scholar in Control and Analytics Process Systems Lab in the Chemical Engineering Department at IIT Delhi. So, in this particular session, I'll be discussing a slice of the extensive work that we do in graph machine learning. So, our this particular work is basically titled as Graph Embedding Based Fault Detection Methods for Multivariate Time Series Data. Okay. So, first of all, yeah, so these are some of the topics that I'll be sailing through during the course of my presentation. And coming on to the introduction part, so as we are very well aware that fault or abnormal behavior can occur to any particular industry, be it chemical, pharmaceutical, or any manufacturing industry. So what we have to do, we do not want these abnormal behaviors to be there in the system. So in a way, we want to eradicate these faults so that we can go towards the smooth functioning of our process. So now process modeling, as we all know, can be done on the basis of two types. One can be data-based approach, and the other one can be first principle model. So what happens in a first principle model, these models are slightly tedious to build, and we have to like take into account all the disturbances and all the other things. Whereas when we talk about the data-driven model, what we can do is we can, from the data, we can from the past data, we can learn like how this system is particularly behaving. So yeah. So this is the general schematic of a data-driven model. So what we have to do is we have the initial training data. Then we build a model. We learn from that training data, and then we apply some test. We have the separated test data, and we apply this model so that we can figure out whether this is anomalous or not. Okay. So now what is our motivation to shift towards graph? Now what happens is graphs are basically they provide us with the ease of visualization. So whatever data sets that we have, in a way, when we represent them in the form of graph, we can store the entire information in the form of nodes, edges, and weights. Similar, a second point regarding it is that all the standard machine learning techniques and deep learning techniques, all these are very much applicable to the graph systems as well. So we are not missing out on any of the traditional approaches. We are incorporating everything, but in a way we are trying to visualize the data and the process in a better way. And the other point is that let's say that graphs are basically mathematical systems. So any problem of this world can be solved by graphs, be it supply chain management or be it process monitoring. So wherever we have the concepts of graph, we can easily apply the graph theory, and from that we can apply the mathematics part of it. So easily we can solve any problem through the graph system. So these are some of the salient features why it has motivated us to shift towards graphs. Okay, so now this is the schematic of the proposed methodology that we are going to follow. So first of all, we can see that we have a, don't know whether it's working. So we have a multivariate time series data set with sliding window. In the yellow part we can see there. Then what we can do is we can what we are doing here is we are taking the data set in a sliding window fashion. So we are constructing the graph based on, we have a window of certain normal points and certain faulty points, and then we are extracting the input graph from it. And then these are the shallow embedding methods, which is in blue and green. So there are two basic methods, and it is done in an unsupervised setting. So what happens is we have the matrix factorization method and we have the skip gram model. So people might be aware that people who might be working in NLP might be aware that there is a model word to vec, which is based on skip gram model. So similarly, we take inspiration, or the node to vec algorithm takes inspiration from the word to vec model, and that node to vec algorithm we try to incorporate so that we can identify the faults. So once we have these two methods, then we generate the node embedding of a particular vector embedding of a particular node. So what happens is that nodes are, if we just visualize it, then it is nothing but a simple structure. But what our main motive is to extract the mathematics that it is hiding. So we extract the node embedding vector, and then we feed it to a variational autoencoder. So variational autoencoder I will be discussing in the subsequent slides, and then we rank out the anomalies. So let's say that a particular value is exceeding a threshold, we count that as an anomaly. Moving on. So now coming on to the skipgram based node to vec. So what happens is that skipgram model, it is basically takes inspiration from the neural network. So what happens, let's say if I take a sentence which is he is pointing his finger towards someone. So we have the context word, we have the target word. So let's say pointing is a target word. So around it we take a window of words so that we can understand the context as well as the target. So we are trying to embed the words into a particular vector. Similarly, we have the nodes. So first of all, we will be having a graph structure. Once we have the graph structure, then what we do is we take a sliding window, and from a particular node, we take a window or walk length of 5 nodes, 10 nodes, or it may vary according to the situation. So from that, we try to preserve the neighborhood of the nodes. So when we talk about the node to vec algorithm, so it tries to preserve the neighborhood so that when we have a target node, it learns the neighborhood of that target node as well. Okay. So then as we can see, node to vec designs an objective that seeks to preserve the neighborhood of nodes, and it is flexible to learn both the structural equivalence and same community nodes. Now this is a very big problem when we talk about structural equivalence and same community nodes. So let's say there are certain algorithms which is spectral clustering for that matter. It only takes homophily into account. It means that it is only tracking the nodes which are present in a particular cluster. Whereas node to vec, what advantage it has is that it not only takes the immediate neighborhood into consideration, but also explores the node which are at a far distance from that particular node. And similarly, why there is another method which is known as PCA. We all are very well aware of it. So PCA, what happens with PCA is we have to calculate the spectral properties of the matrix. So spectral properties are slightly difficult and they are slightly time consuming to calculate, computationally expensive as well. So for that matter, we switch to this exercise where what we are doing, we are also trying to make the higher dimensional data into a lower dimensional space. We are trying to convert a higher dimensional data into a lower dimensional space, and for that, let's say we have a graph which is a subset of, which is a bigger set of vertices and edges. Okay, so V is the set of vertices, E is the set of edges, and this dimension D is the one where we are trying to embed the nodes. So for every source node, so like in the subsequent slides, what we'll be seeing is U will be our target node, that is a source node around which we have to preserve the node embedding, and it is belonging to a set of vertices which is V. So, and S is the sampling strategy. Now this sampling strategy can be node to vec, deep walk, graph to vec. This will be covering in the subsequent slides, and NU is the neighborhood of the nodes. So these are some of the terminology, and now if we look at it, so what we have to do, we have to maximize the probability of a particular node that is near to the target node. So now in equation number 1, we can see that we have the log probability of NSU. So NSU is nothing but this is just the neighborhood sampling strategy is S for that particular node, like the neighborhood of that node, and FU is the feature that we are incorporating. Now what happens in node to vec is basically a very unique way to understand the data, because what happens is that here we do not have to apply any labels. We also do not need any features. Like if you see graph neural networks or graph convolutional neural networks, you also require a attribute matrix, or you can say a feature matrix. Whereas in node to vec, it just learns from the graph structure how and why we are proceeding. Now coming on to this particular part, so now we can say from equation number 3 that we have represented the node I in a feature space, okay, and we take the dot product. So what happens is, if we have to look at the similarity of between two nodes, the very basic feature that we take into consideration is the dot product. If the dot product is higher, we say that they belong to a similar space, and if it is lower, then we say that they are far away from each other. So now the objective function, if you look at it from equation number 4, this is the objective function which where we have to maximize and we have to preserve the neighborhood of the nodes, and this can be optimized by using SGD. So this is about the node to vec. Now what happens is, from the start of all these graphical exercises, we are very well aware that we have two basic sampling strategies. One is the breadth first search and the second one is the depth first search. So in BFS, what happens, we are only exploring the immediate neighborhood of the node, and DFS takes into account the we can say the distant or the far away nodes. But node to vec, what happens is it takes into consideration both the features. It also includes BFS and it also includes DFS. Now how it is done? So it is done with the help of two parameters, P and Q. P is known as the return parameter and Q is known as the in-out parameter. So let's say if we have this node C, which is node Ci, which is equals to x, and the previous node to it was V. So now here we calculate the transition probabilities. So if the transition probability turns out to be a higher value, we say that this will go from V to X, and for that V and X have to be connected in the original space. If they are not making an edge, then we can say that V and X are not connected and it has to be termed as 0. Okay, so the transition probability that we will be taking will be equal to 0. So now if P is greater than 1, the walk moves moves far away from the nodes. So it is a very simple phenomena where P is representing, in a way, it is representing BFS and Q is representing DFS. We are taking both into account, so that's what makes node to vec a special algorithm. Yeah, so now if we look at it, so pi Vx is equals to alpha PQ Tx into WVx. So it has included P, it has included Q, and it has merged it with the transition probabilities. So now the basic thing that we can do here is we can tweak the parameters P and Q according to our situation. If we want to move towards the depth side, we can tweak Q, and if we have to explore the immediate neighborhood, we can tweak P. Now, similarly, there is another algorithm in the skip-gram model only, which is known as deep walk. Now, what happens in deep walk? In node to vec, we were utilizing biased random walks, okay, because we are biasing our model with the help of P and Q, whereas in deep walk, this is just a random walk approach that is being followed. So let's say that we have a graph structure, we initialize a particular node, it can move to any particular direction, we are not controlling it. So this is just a random walk, and now in the last point we can see there is no guarantee that the local neighborhood of the node is well preserved, which has to be the case because we are not biasing it, so it will move in a particular random direction and we won't be able to control it, so we may or may not be able to preserve the local neighborhood of the nodes. Now coming to the other part, as I have already shown that we are going to discuss, so now we are going to discuss about the matrix factorization technique. We have already covered the skip-gram techniques. We have not covered H2vec and graph2vec because we are mainly focusing on the node-centric approaches. So that's why we have taken node2vec and deep walk. H2vec, same thing. We just embed the edge into numerical vectors. So now coming on to the matrix factorization techniques. Yeah. So matrix factorization techniques also help to generate embeddings. Embeddings are just the numerical representation of nodes and edges. Okay. So the only difference is this utilizes a particular loss function. Okay. Here in skip-gram model, we were basically utilizing the random walk approach, whereas in matrix factorization, we are using a loss function. So let's say this is a general loss function of a matrix factorization technique. This is how it behaves. So now if I show you, so the very first technique that comes in our mind is known as the graph factorization technique. So graph factorization, what we do is we have a matrix R V cross V, okay, and this is a weighted adjacency matrix. Similarly, we have the matrix A, which is known as the adjacency matrix. So now once we generate the embeddings, once we have all the dimensions, then yi and yj are just the dimensions that we take into consideration. These are just the column vectors, and yi and all the other columns, and yj and all the other columns. We take a transpose of it, so it turns out to be of a we can say I cross j only. So now lambda is the regularization term. So this is the graph factorization loss function, just a simple loss function. And now another term which is known as higher order proximity preserved embedding. So here what happens is, so as of now we are only talking about the immediate neighborhoods. We are saying that this is the, let's say A is connected to B and B is connected to C. So now hope, this particular thing, hope algorithm also takes into consideration the far away or the distant neighborhood into consideration. So now what happens, this is the loss function which is represented by equation 10, and this is how we find it. So these were some of the algorithms. Now this is the variational autoencoder. Maybe I'm running short of time, so we can discuss it afterwards. So this is used for the downstream tasks. So once we have the embeddings generated, we can feed it to the variational autoencoder, and instead of a traditional autoencoder, what it does is it learns a distribution of all the nodes. So autoencoder in the latent space will only provide us with the single values, whereas variational autoencoder provides us with a distribution. So it is very much easy for us to map that which particular embedding will belong to which particular distribution. So yeah, so this is the loss function of variational autoencoder, where we are reconstruction. We have taken KL divergence is required because KL divergence measures the probability distribution distance between two functions, and these are some of the results. So now we can see that if you look at this figure, so these are the embeddings generated using node-to-vec algorithm, and we have two data sets where we have validated this study. And the very first being the NPCIL data set, power flux data. So there we have simulated, and we can see that all the cluster that is being formed at the extreme left, that is just the normal points which are behaving in a particular pattern, and the faulty points, as we can see, they are following a particular pattern and they are forming a different class altogether. So this is for the NPCIL dataset. Similarly, embeddings generated using deep walk, and this is for the Tennessee Estiman dataset. So these are the generated embeddings. So here we can see that again faulty nodes are forming a different class, and this is forming a particular cluster. So these are some of the results where we found that node-to-vec outperformed all the other methods, like it outperformed deep walk and also graph rep and hope. So these are the results for the NPCIL dataset. For the Tennessee Estiman dataset, this is the conclusion of our work, where we said that we are extracting the graph in a sliding window fashion. Embeddings are generated, and variational autoencoder was used for the downstream task, and node-to-vec performed the best. So these are some of the references, and we would also like to thank the Board of Research in Nuclear Science for funding the project, for funding this particular project, and also IIT Delhi for allowing us to carry out a smooth research, and also PSC and IIT Madras for providing us the opportunity to present our work. So thank you. No. So for this particular case, we have only considered 3 faults: fault number 6, fault 15, and fault 19. Yeah, that is the average we have taken.
So which kind of fault you taken, step or random?
So yeah, so one fault was behaving in a negative direction, that is fault number 6. Fault 15 where the way, like I'll tell you. So yeah, so fault 15 was forming an upward parabola, like from the normal pattern, and fault 19 was just a random noise that we have considered.
Okay. Sure. Thank you.
Okay.
Any other questions?
So, this is all done offline, I presume.
Offline as in?
As in, so when you do monitoring, right? It's all data taken.
Yeah.
And it's not like you're doing it online, as in
Yeah.
data point.
So it is done offline.
So, in the context of an online process, I'd like to ask you the question: what is the difference in time complexities as compared to conventional techniques like CVA, PCA, whatever?
Yeah. So what happens here is we have to then when we are doing it online, we have to form a graph that will be a dynamic graph. So with respect to time, we have to map like which particular node will be connected to another node. So if that particular graph is made in a dynamic manner, then maybe this exercise, because once the graph is made, the algorithm is already there, okay, and then we can generate the embeddings in real time. Or what we can also do is, if we have suppose, let's say if we have a particular window that this is how the embeddings must look like, then maybe a particular model can be trained, and any further incoming embedding can then be traced accordingly. So for that, then it will be a supervised case where you have to know a particular window, and for that window we will be generating embeddings. Any value going beyond or below that particular embedding can then be treated as a particular fault. Yeah. 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 So as of now, we have not considered diagnosis for this particular thing, but definitely it's on the radar. So that we'll be considering.
Any other questions?
Yeah, one more question.
Yeah.
So how you choose the window size?
Window size. So we didn't apply anything like any particular methodology to it. So what we did was, let's say if we are considering 50 points and a window of let's say 15 to 20 points, so we decided on a window of 10 points, okay, so that it can easily scan. So in node-to-vec, I'll tell you that if a window size is of 5 nodes or 10 nodes, it won't make a difference. Only when let's say if it is of 5 and 50, then it will be making a difference, because that will be a graph in itself.
Sure.
Thank
So that will be the case.
Any other questions? If not, we. Last question.
So in the graph, so the nodes represent the variables, is it?
So sir, here the nodes represent the time steps.
So time.
It is a time series data. So the variables are there, and for that particular time step, it has already extracted all the variables. It has already taken into consideration.
So it has taken multi-variable. It does multivariate.
Yeah. Yes, sir.
Okay. Thank you.
Okay. Thank you, sir.
Thank you once again.
Thank you, sir.
And